If you've ever used Python for any kind of math, chances are you've run into SymPy. But today, we're skipping the basics. We are diving deep into some of its most powerful and frankly coolest features for advanced mathematics. Let's get into it.
So, when you think of SymPy, you probably think of simplifying a basic expression, right? Or maybe solving a simple equation. And hey, it's great for that. But if that's all you think it can do, you are barely scratching the surface of what's possible.
Because hiding just beneath that simple interface is an incredibly powerful engine, one that's packed with tools for tackling really complex problems. So today, we're going to pop the hood and unlock its true power.
Here's our game plan. We'll start with the foundation, the algebras module. Then we'll get into mastering symbolic matrices. After that, we'll take a really fascinating detour into quaternions and 3D rotations. And finally, we'll learn how to make SymPy even smarter using assumptions.
Okay, first up, the SymPy.algebras module. You can think of this as the central hub, the absolute foundation for all the advanced stuff we're going to talk about today. Everything else builds on this.
And here's why this matters. This module is what turns SymPy from a single calculator into a real mathematical partner. It gives us the language and the structures we need to define these higher-level concepts. It's basically our gateway to working with complex things like matrices and quaternions, which we're going to jump into right now.
All right, with that foundation in place, let's get to the main event, symbolic matrices. Seriously, if you're doing any kind of linear algebra, this is your Swiss Army knife. It's just so versatile and so powerful.
What's great is that SymPy supports your entire workflow. You can spin up matrices in an instant using functions like I for an identity matrix, or zeros for a matrix full of zeros. Then, you can dig in and analyze them, find the determinant with det, check the rank, or get the norm. And finally, you get to manipulate them with all your workhorse functions, like inv to get the inverse, or solve to crack a system of linear equations. But what's really incredible here is just how deep the toolkit goes. I mean, look at this. It's not just about having one way to solve a problem. You've got LU decomposition, which is fantastic for solving a bunch of systems that use the same matrix. You've got QR decomposition, a total go-to for least squares problems. For certain symmetric matrices, you've got Cholesky. Look, you might not use all of these every day, but just knowing they're in there, well, that tells you this is a serious library for serious engineering and physics.
And this right here perfectly illustrates why having specialized tools is so important. On one hand, you have solve. It's precise, it's direct, it's perfect when you have a clean system, like calculating the forces in a perfectly stable bridge. But what about when things are messy? Imagine you have a dozen noisy temperature readings from a sensor, and you need to find the trend line. There isn't one perfect answer. That's where solve_least squares comes in. It finds the best possible fit for all that messy, real-world data. SymPy gives you the right tool for the job.
Okay, so we've seen how SymPy handles the wide world of linear algebra. Now let's zoom in on something a bit more specialized but unbelievably powerful. 3D rotations using quaternions. If you're in 3D graphics, or robotics, or aerospace, you know that calculating rotations can get really, really hairy. Quaternions are the elegant solution.
So, what on earth are they? Well, a quaternion is basically a four-dimensional number that builds on the idea of complex numbers. But here's the important part. In practice, they are an incredibly efficient way to represent 3D rotations that avoids major pitfalls like gimbal lock. That's a nasty problem where you can lose a degree of freedom, which is a total nightmare in animation or flying a spacecraft. Quaternions just sidestep that whole issue.
And SymPy makes using them surprisingly straightforward. You can create a quaternion just by giving it a rotation axis and an angle. You can easily convert it back into a standard rotation matrix if you need to. You can even use it to directly rotate a point in space. It's all there. This is some seriously powerful stuff made easy.
All right, for our last stop, let's talk about how to make SymPy even smarter. This is where the assumption system comes into play. You should think of this as giving SymPy helpful hints, a little inside information, so it can reason about your math more effectively. So here's a classic problem that trips up pretty much every new user. You type in the square root of x squared, and you're expecting to get the absolute value of x back, right? But SymPy just gives you the same thing back. Why? What gives? Well, without any hints from you, SymPy has to play it safe. It doesn't know if x is a real number. What if it's a complex number? In that case, the rule doesn't work. And the solution is the assumptions system. This is where you get to give SymPy that missing context.
You can tell it facts about your symbols, and when you do that, you allow its simplification engine to use rules that would otherwise be unsafe. You basically unlock more intelligent, more accurate results.
And you can be incredibly specific with these hints. You can tell SymPy a variable is positive, or real, or an integer. You can even tell it that a variable is prime. So if you go back to our problem and tell SymPy that x is real, then boom, the square root of x squared simplifies to the absolute value of x, just like you'd expect. It's like you're collaborating with the engine.
So, let's wrap this up. What's in our new takeaway toolkit? Well, we've seen that SymPy's matrix class is an absolute powerhouse for any linear algebra you can throw at it. We've unlocked the magic of quaternions for smooth and efficient 3D rotations, and we've learned how to supercharge the whole symbolic engine by using assumptions. This is SymPy at its very best.
So the next time you fire up SymPy, just remember you've got these secret weapons ready to go. They can help you model incredibly complex systems, simulate physical phenomena, and solve problems that you might have thought were way out of reach. So the only question left is, what impossible problem are you going to solve now?